So Vijoy, is this the famous chip?
You bet it is.
Good.
So it's like, and that's the packaging that you see.
Yep.
It's in blue,
Yeah.
but the chip is right in the center, in the middle of it. And it's maybe one half the size of my thumbnail.
Oh, wow. Vijoy, the question that always comes up with quantum, right, is we talk about quantum safe encryption. People are worried that encryption is going to be broken with quantum. Is that kind of related to that, to this? Is it like one of the use cases, or how does that fit into this?
So there are two ways to look at that.
Yeah.
Right. So on the one hand, what we're trying to do with this chip is we're trying to accelerate the timeline for practical quantum computing. The one thing that we are super excited about in quantum networking is that there are use cases of quantum networking using this property of entanglement and teleportation in the classical world today. Think of these medieval era where an enemy is approaching and I'm sitting on a hill. You see, somebody sees enemy approach and somebody runs around your horse and carries a banner says, the enemy is approaching. And the amount of time it will take for that person to come to you versus you have all of these cauldrons on top of a hill and everybody lights up their cauldron to say the enemy is approaching. The difference is just
Huge. Yeah.
phenomenal.
Hey everyone, David Bombal back with Vijoy. Vijoy, great to have you back on the show.
Pleasure to be here, David.
I got to ask you about this technology. It seems to be the next big thing. What chip have you just released?
So this is a quantum network entanglement chip.
Okay, you gotta tell us what those words mean.
Yeah, exactly. It's a mouthful. In fact, there was the earlier version of the name was the quantum network entanglement source chip. So we shortened that down to just the chip. But it is the beginning of quantum networking. It is the building block, the first building block of a quantum network. And I can dig into details of what this is, but let's start with what it tries to achieve.
Okay.
And so if you think about quantum computing today and where it's headed, one thing that you must be seeing is like the number of announcements and the progress of innovation is actually just accelerating. And this happened in the AI space as well. You went from the 60s when neural networks were discovered or invented to 2022, the ChatGPT moment, and then now, which is like, we don't even know what's going on. I mean, it's just exponential in nature, right?
Yeah.
The same thing is happening with quantum. I mean, it was slow for a while. You were seeing these innovations happen every few years, then few quarters. Now it seems like it's every month or every few weeks. And that's the exponential trend that's happening on the compute side. But what they're trying to do on the compute side, like everybody else, like the IBMs and the Googles of the world, they're trying to build bigger and bigger quantum compute nodes. So this is like taking a server in the classical sense and making it bigger and bigger, like a behemoth, right? We, Cisco, are a networking and security company. And we also know that the way you scale things is not by scale up, but by scale out. That's the whole thesis behind cloud.
Yep.
So distributed computing is a bunch of servers tied together through a network, secure network. And so we're trying to do the same thing with quantum computing. We're trying to tie quantum compute nodes through a quantum network to be able to drive scale out systems, and accelerate the timeline for practical quantum computing by 5 to 10 years. Because currently, if you think about quantum computing, the pragmatic numbers that you see being thrown around is we need 100,000 qubits, or we need 1,000,000 qubits. And we are at 150, 200 qubits.
Oh, wow. It's a long way to go.
So like in 5 years, we'll get to like a couple of thousand, right? And so how do you get to hundreds of thousands? The network. Because you'll be able to connect all of these things and make one distributed quantum computer. And that's what this chip, the first step towards that goal is this chip.
So Vijoy, is this the famous chip?
You bet it is.
Good.
So it's like, and that's the packaging that you see.
Yeah.
It's in blue.
Yeah.
But the chip is right in the center, in the middle of it. And it's maybe one half the size of my thumbnail.
Oh, wow.
Okay, small chip.
Yep.
Mighty, mighty power and what it can do.
Yeah.
So it is actually generating 200 million entangled photons a second.
Wow.
Photon pairs a second. And it's sending it over these fibers that you see coming out.
Yep.
And the copper wires here are the controls that you send to the chip.
Okay.
And the whole idea is that you generate these photonic pairs, entangled pairs. You send it to point A and point B, Alice and Bob. They each get one part of the pair, and they impose their quantum state on that photon. And after that, it's quantum teleportation.
It's amazing.
So you get to see what I get to see instantaneously.
So I'm assuming these are like standard fiber cables, right?
Yeah. And so one of the big things that we embarked upon when we were creating this chip is we want to build something that operates in real world environments in the world today.
Yeah.
So the 200 million entangled pairs of photons that it generates, they are being generated at telecom frequencies.
Wow.
So you can use existing fiber, you can use existing infrastructure within the data center and across data centers, and this chip operates at room temperature. So you don't need those massive cryogenic cooling systems to make it work. It can literally work in the environment it's in right now. And so you can deploy it at scale. It's really tiny, it's low power.
Yeah.
You can stack a gazillion of these and you can operate it at room temperature on existing fiber. So you can deploy it today at scale. But this is a research prototype.
Yeah.
And so we are actually figuring out what use cases make sense in the classical world today. And when we have a good handle on some of those use cases, then we will go into production.
I think some people might be confused. Is this quantum computing or is this different to a quantum computer?
So this is quantum networking.
Yeah.
And so quantum computing is creating those servers that we are so familiar with in the classical world. And so you use a network to connect a bunch of servers to get to distributed classical computing or the cloud that we all know and love. And that's the scale out deployment pattern that we are familiar with. Nobody builds these massive singular servers anymore.
Yeah.
It's the same fundamental principle here. So we as Cisco are in the networking business.
Yeah.
We are not going to create these large quantum compute nodes, but our goal is to create a quantum network that you can use to tie and connect these relatively small quantum compute nodes and build out a distributed quantum compute environment or a compute data center, a quantum compute data center.
Love that.
This is actually to connect all of those quantum compute nodes together.
Is it vendor proprietary or is it like an open thing that can work with all kinds of vendors like Dell or whoever creates a server?
So I would answer it in a different way. There's a lot of IP in this chip.
Sure.
So it's not open in that sense, but it's...
But open standards to connect to a server, right?
We're working towards the standard. So we're working on the protocols. We're actually going to open source a bunch of the control software as well so that we want to drive adoption of these things. But the way I would answer that question is like there are a certain number of physics technologies that are being used today, ion traps, transmon, and so on, for the quantum compute nodes themselves. We are being agnostic to that.
Okay.
So what we're saying is, just like whether it's Spark or x86, the network was agnostic to those technologies.
Yep.
In the quantum realm, we are being agnostic to the physics technologies that exist. In fact, we're handling that complexity at the edge. But the network itself will be telecom frequency, existing fiber, room temperature, connecting anything out there.
Amazing. Vijoy, the question that always comes up with quantum, right, is we talk about quantum safe encryption. People are worried that encryption is going to be broken with quantum. Is that kind of related to that? To this? Is it like one of the use cases, or how does that fit into this?
So there are two ways to look at that.
Yeah.
Right. So on the one hand, what we're trying to do with this chip is we're trying to accelerate the timeline for practical quantum computing.
Okay.
So instead of building, again, these monolithic large quantum computers, where you would take 5 years to break current encryption, at least key exchanges.
Yeah.
Using a network, now you can build a distributed quantum computer, and we are accelerating that timeline from 5 years to something sooner. So in some senses, it's accelerating that timeline. And so you should be paranoid that some of these encryption mechanisms will get broken sooner. On the flip side, you can use this exact same chip to protect against some of those attacks. And the way you do that is by leveraging some quantum properties. So this chip, like I said, is generating entangled pairs of photons. And let's say you're Alice, I'm Bob.
Yep.
You get one of those photons, I get one of those photons. And we are in the quantum realm, and we are actually entangling ourselves in the quantum realm.
Yep.
If there's an eavesdropper that comes in and actually snoops the traffic between the two of us, inadvertently what that eavesdropper has done is they're going to collapse the quantum state between the two of us, that photonic state. They're going to collapse the state, so both you and I will know instantaneously that there's an eavesdropper in between. So on the one hand, yes, we're accelerating the timeline for practical quantum computing and to the breaking of these key exchanges. On the other hand, you can use this today to safeguard your communication, even in the classical world today. And we're calling that eavesdropper-proof security.
So if I understand this right, like in classical computing, we use public and private keys. Is this used in addition to that, or is it replacing it, or how does that work?
So this is like difference in depth. So you would use it in addition to what is going on right now. So you can also say, and let me assume that we are just using standard TLS.
Yeah.
Diffie-Hellman, RSA, key exchanges. Using this and making sure that there is a photonic entangled pair between the two of us, I can detect eavesdroppers in the middle. So this class of attacks that we are all worried about, where it's store now, decrypt later,
Yeah.
I can tell if there's somebody in there trying to store things now using this chip. Now, you can do that with classical TLS, Diffie-Hellman, RSA. You can do it with the new NIST standards, the PQC, post-quantum
Yep.
cryptography. So that's another layer, but you can still use this to make sure that it's bulletproof. Or you can go all the way and say, I want to do quantum key distribution, which is like the ultimate holy grail. But this is great even to start out with and make it provably quantum secure.
This is not available commercially yet.
It is a prototype, and we're working through some of these examples like
Yeah.
eavesdropper-proof security, decision coordination. Think of decision coordination as a starting gun that everybody across the world can hear at the same time.
Yeah.
The use cases are just mind-boggling. And so time synchronization for large cloud databases,
Yeah.
position verification, all of these use cases in the classical world today, we're working through some of those. As we get a good handle on some of those use cases, we will start producing this at scale. But right now, it's a research prototype.
Entanglement, you got to explain that, because I don't think a lot of people know exactly what that means and why it's such an important thing.
Yeah, so if you think about the quantum physics, and I'll try to keep it as high level as possible because you go deep and everybody's head hurts. In fact, I heard a quote from someone which said, if your head doesn't hurt understanding quantum physics, then you're not understanding it enough.
I like that.
So entanglement is a property at the quantum level where some property like an electron spin or a photon polarization vector between two particles is one and the same.
Yep.
And so it's almost like they're in kumbaya. And so if I change the electron spin on one of them, the other one automatically changes instantaneously. And distance between these two entangled entities does not matter when that change happens. So in our case, what this chip does is that it generates photon pairs, photon A and photon B, that are entangled. So their polarization vectors, for example, are one and the same. And so if you change the vector on one end, the other photon will change its vector instantaneously. So they're entangled in nature and they're dancing together. So that's what this chip does. And the process by which this happens is actually known as quantum teleportation.
So you got to explain that. When you give that to two servers, they could be far apart. Like I could be in England and you could be here, and that property changes instantly between them. And what's the use case of that?
So many use cases. So let's start with the vision that we have. So the vision that we have is to create distributed quantum computing data centers, so to speak. And so where you have all of these individual quantum compute nodes all sharing the same state. Now, in classical sense, the way you exchange state and share state in a cloud data center, for example, is you and I are exchanging state information to a standard classical network where I'm sending bits from me to you through a data center network. And the bit traverses all the way, comes to you, and now we have the same state across you and I. And so logically, you and I are behaving like one compute element, and that's how we compute. The quantum network is very different compared to this. So instead of sending bits, first of all, quantum nodes operate in qubits or quantum bits. And the way we need to exchange state is making sure that you and I are in the same quantum state at the same time, not the classical state. So to do that, what this, for example, this chip does is it'll send you a photon, an entangled photon, and the other pair comes to me.
Yeah.
The other part of the pair comes to me. And when I need to change state on my end in the quantum realm, I mean, this is key to point out because there is a speed of light issue that we'll talk about in a second. But in the quantum realm, when I'm changing state of my photon, since yours is entangled, you are getting that state change instantaneously, whether you're sitting in England or Tokyo, or it could be anywhere in the universe. Practical considerations aside. So that's what it does. So it makes sure that you and I are in the same quantum state. So that way we are computing on the same logical quantum state, and we are one logical quantum node.
So in other words, if I did some kind of encryption or something, we're in the same state. We don't need to do anything extra. Is that right?
Right. So if you're computing an algorithm, which is a quantum algorithm, and if you're changing the state, not just for one photon, but a series of photons that capture state, whatever you are doing, you're imparting that state to those photons, and I will get to know instantaneously what you've computed, and vice versa. So that way we have a set of photons on which the algorithms that we are running in parallel between you and I are actually being shared instantaneously. So you and I can be acting on the same algorithm at the same time, no speed of light issues in this situation. Now, when I want to retrieve that state as a human in the classical world, we still have to go back to speed of light. So information retrieval in the classical world is still there's still a hurdle of speed of light, but in the quantum realm, it's actually the same. So let me give you a pretty concrete example of where this is relevant today. So we've been talking in abstract terms in quantum computing and how distributed quantum computing works. But the one thing that we are super excited about in quantum networking is that there are use cases of quantum networking using this property of entanglement and teleportation in the classical world today.
Yeah.
So a simple example is high-frequency trading. And there's a whole class of use cases we call decision coordination. Think of these medieval era where an enemy is approaching and I'm sitting on a hill, my fortress is on top of a hill, and you had these, I don't know if you've seen Game of Thrones or other medieval shows or movies, and you have all of these hills with a fire cauldron. And what you could do is, somebody sees enemy approach, and somebody runs around your horse and carries a banner says, the enemy is approaching. And the amount of time it will take for that person to come to you versus you have all of these cauldrons on top of a hill and everybody lights up their cauldron to say the enemy is approaching. The difference is just
huge,
phenomenal. So in HFT, what we say is, let's say there is a data center in New York City and there's a data center in New Jersey. And there's information that I want David, you, to act upon in New York City, and Vijoy needs to act upon in Jersey, but we need to act upon that data at the same time. You cannot guarantee that fairness through classical means because
even with fiber,
even with fiber. And let's say we start stretching that across the country.
Yeah.
You cannot guarantee any of that. But if we had a starting gun, which you and I heard at the same time across the globe, across the country, then that would be fairness. So that's decision coordination. An entangled photon between you and I, just one, can do that job, as an example. There are other use cases like synchronizing clock. So you have these really large cloud databases across the globe. How do you make sure that you have asset properties like they are in sync and they are operating at the same time domain? You can do that by using this mechanism. So there are many use cases that operate on this. The other use case that we talk about is if we were to measure it, you would collapse that state and get back to classical. So if somebody measured that photon, it'll collapse back to classical world and it'll pick one of the polarization vectors. So that teleportation effect is gone. So we use that property in security. We use that property to do position verification. But there are a whole bunch of these use cases that are possible in the classical domain today that you can leverage the quantum network for. And that's exciting us a lot more. And by the way, it's less than a milliwatt and it's relatively cheap to produce. I'm not talking about pricing. I'm talking about tech here. But all of these properties mean that you can create thousands and thousands of these to operate at scale, at room temperature, on existing fiber, and not worry about rip and replace anything. That's one thing. The other thing that we're doing is, yes, this fabric and this chip operates at room temperatures. This is just the step one. There are many other steps that we need to talk about. But if you think about the things that it's trying to connect to, is these quantum nodes. Now, those quantum nodes, there are like 8 plus, 9 plus technologies out there. Trapped ion and there are so many of them. I don't even want to get into those. But how do you bridge the gap between that and the cryo temperatures there to this fabric. So the way we are designing the data center fabric and the network in the quantum domain is we are pushing that heterogeneity, that complexity to the edge. So we are creating these interface cards, which are frequency converters that convert from those quantum computing technologies to room temperature, telecom frequencies at scale, at the edge, at the interface card. And from that point on, everything is homogeneous. Room temperature can work on existing fiber in the infrastructure you have.
I'm a grumpy old network engineer, like a lot of old network engineers. We've been promised quantum for a long time, just like other technologies. You know, we were talking like things are happening more often now. When do you think it's going to be a reality, like where this stuff kind of gets deployed and out of the lab?
So I think on the quantum computing side, we've already seen some companies talk about real world use cases. But there are struggles around scaling it out, like we just discussed, and where we can come in and help. But there are also struggles around operability, because today, if you want to scale those things out, you're scaling the cryo domain per se to scale it out. And that doesn't bode well for operability, because if you want to repair or upgrade even one tiny part of that ecosystem, you need to bring everything down and then bring everything back up again, which is not an instantaneous thing to do. So I think there are some pragmatic challenges in scaling those things out. That's where we come in. So I think that's why we keep saying that we are accelerating that time horizon by 5 to 10 years. But the quantum network, I would say the chip is pragmatic, practical, usable today. It's still a prototype. The thing that we just announced is a prototype. We are working with some design partners for some of these use cases in the classical world, like decision coordination, clock synchronization, position verification, and eavesdropper proof security, those 4 big use cases. Once those are proven out, I think we are ready for scale, because I don't think it's a technology building block problem. There's some more things to build. Like, for example, we are working on a switch, quantum switch. We are working on the protocols that are needed and the controllers, the software controllers that are needed. So you do need to build everything from the ground up. So that's happening. But I think once we have some of these use cases that we just described in the classical world, which are here and now, I think we're ready for scale. So I can't predict an exact timeline, but I can touch and feel and smell it.